Hey everyone, welcome back to my side project. This is the Think Like A Postgres Part 2 video. If you haven't seen Part 1, it should be available on YouTube probably very close to where you found this video. So, I don't know, Google that? It's probably not the right verb. Anyways, in the first part, for those who missed it and haven't checked it out yet, you really should go look at it. It sort of sets the table for the things we're going to talk about in Part 2. There we focused on storage, and we talked a lot about these magic 8K pages, and sort of brought together how Postgres deals with storage, and what it thinks about storage, and how all that interacts between tables and indexes and whatnot. And so hopefully you recall these printouts. This is an 8K page, in case anyone's wondering. And we get into that quite a bit in part 1 of the video, so please go check that out first, and then come back here and join us for this next bit. Alright, so let's talk about indexes. We hinted at it in the first part, and let's get into it now. So the main thing you want to start thinking about when you start thinking about making indexes on your tables, right? This is a common part of database operations. Anyone who's written queries, you get into this sooner rather than later in most cases, on any type of database actually. In Postgres, when you make indexes, it's very similar to the idea of just basically making copies of your data, and it works at the storage level very similarly to how tables work, at least from the sense that Postgres still thinks about everything in 8K pages. If you go ahead and run a command like the one we have in front of you, create index user's last access ID, we're going to create that on the last access date first, then on the ID column. Postgres is going to make a copy of that data from our table and store that in 8K pages on disk inside of the index object. And again, you can think of it kind of like what's on the screen, but for bonus points, think of it like an 8K page, just like our heap table. Right? So we would have stacks of pages that are now from the table, and now another stack of pages that would be from our index. The big difference, of course, is that in the index, we are storing those columns in the order that we want. If you remember, in the heap table, Postgres is just writing stuff into that table pretty much as fast as it can, wherever it can find space within its stack of pages. In the index, we're saying, no, we'd actually like you to sort this data in a specific order based on these columns that we've chosen. So you have a subset of the data based on the columns you've picked, and then store those in a particular order based on the data within those columns. And typically the reason people do this is for performance purposes. Right? We add these indexes in based on, well, it kind of depends. Some people do it based on the queries they're going to run, which is really the right way to do it. Other people seem to do it on statistical information about their data, and we'll talk about why that doesn't always work a little bit as we go through this. But it's typically also done to speed up select queries. It can be done, and it will work for speeding up insert updates and deletes as well, but usually people do it when their select queries are too slow. Once we've created that index, we have a second copy of the data, right, stored in that separate set of 8K pages. And you could almost think of it like hyper-local replication, right? So, and what that means is any updates that you do to the table, you now have to also do to the index. And those will be done for you. That's something that Postgres handles behind the scenes. And like replication, it does that in concert. So you just update the table, and it'll update the data in the table, and also update the data in the index. Now, that's important to remember and to understand, because once you've added an index, you're actually creating more work for Postgres to do anytime you want to write into the system. When you do an insert, it's now no longer just an insert into the table, it's also an insert into your index, right? It's twice the amount of storage work. The same thing is true for deletes. You now have twice the amount of storage work that's going to happen for your delete statements. In part 1 video, I had mentioned, I don't think it's world breaking, but I said, having to do more work sucks. So if you're going to do more work, well, let's talk about why we may want to do more work. First off, let me say, I've been doing database consulting for, I don't know, a good 20 years now, focused on Postgres. And I will tell you that numerous times in my career, I've had clients come in and talk to me and want to work with my team. And one of the things that we hear often is clients complain about slow storage, right? We're not writing that much data, but everything seems very slow when we do it. And how do we speed this up? Do we need to buy new systems? Like, can we optimize this? What's the deal with that? And we look, and in theory, they may not be writing that much data, but sometimes we'll look, and on those tables, they'll have like 20 or 30 more, indexes on a table. And again, so that one insert that they're going to do, that one row of data, isn't just one row written into the table. It's now, 20 or at least a dozen times more, 20 times more, something like that, more writes that have to happen on the insert. Same thing with delete, right? So instead of just deleting off of one page within the table, you're now deleting, you've got to modify dozens of pages across the different indexes that are involved in order to handle that right. And so all that extra work, Postgres has to do that work when you've added all these indexes. And there's no way around that. It has to happen, in order to keep everything in check and keep the system running. So that's something you have to consider. The thing that usually falls out from that is, as the person who's running the system, right, if you're a DBA on a system and trying to get the best performance you can, that usually translates into thinking that, hey, if you want to do the work that you need to get done, right, you want to handle the query load that you're going to handle with as few indexes as you need, right? Not as few indexes as possible. Obviously, we could just remove all the indexes. Postgres would, at least in theory, still answer our queries. But you want to do it with as few indexes as needed so that you aren't wasting that extra resources handling indexes that you didn't need. More indexes you add, the more stress you're going to have on your storage. There's just no way to get around that. Also, it's worth remembering that when you add indexes, and the more indexes that you add, you're also making the size of your database bigger. Right? It's not double, so if I add like the index that we just had, we've only picked 2 columns out of there. Right? So we're not like doubling the size of our table with one index. But if you add enough indexes, right, it's going to grow every time you add an index. You're going to need more storage to handle the same number of rows. If you have limited indexes, right, so for example, our 2-column index, that we've got, if you had one index with 2 columns on it versus, 10 indexes or one index with 10 columns or what have you, the more limited those indexes are, the number of them or the columns within them, the more rows you can fit within an 8K index page. And that's important, right, to manage the size of those indexes because they're making everything bigger within your database. And when you make that stuff bigger, obviously that has downstream effects, right? Your backups take longer, you need more memory, it's more storage work, all of those kinds of things. So you always want to kind of keep an eye on that as you're building these indexes out, right? And as you see your storage needs increasing. Now you'll maybe notice I mostly talk about inserts and deletes here, and some people would say, well, what about updates? Like those, obviously you would say those must also affect storage, and they do. Updates are a little more complicated though. Well, maybe they're a lot more complicated, but we'll keep it simple here. So in the simple case, when you update a column, you change the data. So let's say like a last access date. You change that last access date for a given row. You update that row in the table, and then you go update the corresponding index entry, right? And you have to essentially mark the old row as no longer valid and put the new data value in, right? So that's kind of like an insert and a delete. I guess really delete and an insert. It's very similar to doing that process. So it does mean more writes. Just like it would mean, it's extra writes for inserts, it's extra deletes. Well, on an update, it's inserts and it's like an extra insert delete as well. So it is more writes. But some people say, well, what about if I add an index on a column and then we update a different column that's not included in the index? Does that data change? Does that increase the overall workflow? Well, if you watch part 1, you'll remember that I had said that in our heap column, we have some metadata. In our heap page, we have some metadata columns. In particular, I'd included on the paper, there's a ctid and an xmid that are in there. And there's other ones as well, but again, we're trying to keep it simple. The seated column is a pointer to the physical location within the heap, right? So Postgres can use that to say, oh, I know which page within my table that given row lives at, and where, within that page it goes as well. So Postgres uses that as a physical pointer for that. Indexes in Postgres also have a seated. And you might say, well, why have the extra hoop pointing back to the heap? We have the data. Why do we need the seated? Well, the reason why, we have to talk about something called multi-version concurrency control. And this is a mechanism that allows multiple users to interact with the same data, right, as the transactions are going concurrently. It's a non-blocking system, right? So somebody can be updating while somebody else is reading those same rows, and all of that can be going on at the same time. That's great for performance, but obviously there's going to be trade-offs. In the heap page, right, in our heap pages, when we do that, what ends up happening is we can sometimes have two rows of the same data, right? The same row, at least in theory, the old version and the new version. With enough concurrent transactions going on, it's possible somebody is able to see the old version without being able to see the new version, and vice versa. So we can kind of end up with two rows at the same time within our storage system. Now, Postgres tries to optimize all this way. It hides most of this from you as a developer. When you're running your queries, you don't see any of this going on for the most part. And it tries to optimize this extra bit of write activity using a technique known as heap-only tuples. And those kind of sets up a chain of pointers that will lead you to where, from the old data to the new data underneath the hood. So it makes it much faster to look this up. However, sometimes when that happens, you still end up moving data within, from one page in the heap to another page in the heap. And when that happens, the seated of that row is going to change. That means we then have to go update the seated in the index page. Yikes, right? There's a lot of other optimizations that go on here under the hood. I don't want to get too deep into the weeds on that. There's obviously plenty of documentation on this, and it's a technique that's been used and has been enhanced over the years. Heap-only tuples started in Postgres 8.3, so that tells you how long ago that particular thing started. And it's been improved ever since and added to and whatnot. So there's other optimization going on, but here's some key takeaways I want you to understand with this. Anytime you add an index onto your table, you have to think about the write load that's going to happen. The more often the values change within an index, right? So if you're changing the indexed values, the less likely it can be optimized. It's just more difficult to that. In an ideal world, if you had things like that, you would tell people, hey, go back to the heap to get that data, right? But obviously we don't live in an ideal world. So you have to think about that. Our sample queries that we've used so far have generally been on last access date. That is something that you can imagine would change often. Every time somebody logs into Stack Overflow, they've got to update that column. So that changes often, but as you can also imagine, a lot of queries and reports and whatnot are run, and they actually care about what the last access date was, as we've seen with some of the simple queries that we've used. So sometimes it's needed, and if it's needed, right? But let's just understand that we are increasing the amount of work that we're going to have to do, and we're making Postgres' life harder by making it do that extra work. Of course, if you can throw money at this kind of a problem, or throw hardware at it, right, whichever version of that you think it is, whether it's cloud hardware or spinning Rust or what have you, all of this becomes less of an issue, right? If you can just go buy more RAM, maybe it's okay that you've created all these indexes that take up more RAM. So there are trade-offs in the system. Just remember that. There are trade-offs in that system, and, again, money hardware can make that easier. Otherwise, you have to keep these things in mind as you're building out your databases. The corollary to that, of course, is that does mean that fewer indexes is better for performance, over the long term. And like I said, you want as few indexes as possible to support your workload. We can't do no indexes, right? Then every query is a sequential scan. Like I said, Postgres will probably still answer your queries, but that's not the right answer. And the flip side, too many indexes, you'll definitely start to see inserts, updates, and deletes doing an excessive amount of writes, which will slow down those types of queries. So, hey, life is a series of efficiency through-and trade-offs, especially database life. So, okay. Why don't we get back to our select query, and let's talk about how this works with the index. All right, so this is, we've gone back to this version. We're going to get rid of those extra columns for now. Just let's keep it simple and talk this one through. We have our query, select ID from the users, where our last access date is greater than March 11th of 2020. And we want that ordered by last access date. So if I ask you with this query, now that we have an index, how would you go about getting the data to answer this, right? The plain English version, not the nerdy linked list version. But how would you, as a person thinking back to that supply closet example, how would you go about getting the data for this? Right? We have the data in the heap, and we have the data that we need in the index. Right? We have last access date and ID over there. So how would you describe that in plain English? Well, what you might do is something like this. This is one way you could do it. Go ahead and grab your index, right? Grab the pages from your index. Got those right here, right? Pick up this stack of pages, and then we just kind of scan through those, looking for the last access date until we get to March 11th of 2020, and then we just read out the ID numbers in order. That would do it, right? That's all we've asked for is the ID numbers in last access date order. Easy peasy. If we look at what Postgres does, right, here we're going to run an explain analyze and take a look. We see that it does something called an index-only scan, and that basically means exactly what it says. It scans only the index in order to get the answer back to the user, right? And the nice part about this is we're back to a single operator. In the first video, remember I said each of these different pieces are like little programs that fit together, and you can put them together and make sort of longer chains. Well, when we get back to one single operator that runs, obviously it's easier to reason about our query. So here we do an index-only scan. There's a piece of information that Postgres gives us says this heap fetches 0, so it didn't have to go to the heap at all, didn't have to go to the table. It was able to get everything it wanted based on that. Right? And that's pretty ideal. That's, as they say, the chef's kiss. Okay? The other thing I want you to look at here is notice that the cost is also below 100,000. That's better than I think anything we've seen so far, right? In our query bucks measurements, we're down under 100,000 query bucks, so that's pretty good. And so everything about this seems to be clearly better, but let's go ahead and talk about why it is better, just to make sure you understand everything that's going on here. Now, one thing, Postgres, it's kind of funny. So Postgres likes to call itself the world's most advanced open source database, and I think is the caveat of open source, I guess, is that if it was really the world's most advanced database, it probably would have a query hinting system. But, yeah, Postgres doesn't have that. So what it does give us, though, are these like big sledgehammer dumb knobs that you can turn on and off that you can use. And you probably, as you get into more performance tuning and sort of query work, that as you get into that, you'll have to start using these because there's really no other option. Thanks, Postgres. But here what I'm doing is I'm going to set a parameter within my session that essentially turns off index scans. And it's not exactly, I guess you could make the argument, this isn't a hint. I mean, it's not a hint because Postgres doesn't do hints. What this is like, this is your spouse saying that, hey, the garbage has to go out tonight. That's not a hint, right? It might sound like a hint. It's not a hint. The garbage needs to go out tonight. So what we're telling Postgres here is, hey, turn off index scans, right? You just ran this query. You said the index-only scan. I don't want you to use an index for this. And so it will make a shot at not using an index for this. And when we do that, what we see is we actually get a cost in here that is now 640,000. that's quite a bit larger, right? We're back over 100,000. Running the explain plan again, that's what we get. And you're like, hey, what? So just to refresh your memory, right? What is that all about? So cost is this approximation of CPU and I/O work, right? Based on a number of settings that Postgres has to try to model those behaviors. So we know, looking at this, right, comparing these two plans back to back, in our original one where it's, again, we're at 640, and the new one we're at 88,000, well, we know we've eliminated the I/O work, right? That original one had a sort in it. That's no good. It had the sequential scan on the users table, so it had to read everything in the users table, sort all that data. That's a lot more I/O work for sure. And the CPU, right, like now we're just reading the data in order because we have it in an index. We basically paid that CPU cost ahead by creating the index in the order we're going to need. And so now we're just going ahead and we read an order. We don't have to sort anything. So it's obvious that this, is a much better plan, a much better way to answer this query once we have the index available. And that's good. There's another thing, though, you may not have noticed. And this really throws people coming from other systems quite a bit. In the first video, again, I said one way you can take a look to try to understand how much work is Postgres doing or why it's behaving the way it is. Often we'll look at the buffer count in seeing how much work, how much I/O work specifically, does Postgres either think it's going to need to do or actually does. And in here, notice in that first query, so we're back at, 178,000, 180,000-ish buffers are going to be read. So some of that's coming from the buffer cache for Postgres, some of that is coming from the file system, right? So it's a lot of buffers. The weird thing, though, is if you look at our index-only scan, the buffers that it's telling you is over 2 million. And I've done the fancy formatting to make that easier to read, just in case you weren't sure. Because you say, hey, wait a minute. How can sequential scanning the table be 200,000? The table's bigger than our index. How is the index over 2 million buffers hit? Right? What is going on here? Well, again, remember I said those heap pages have metadata columns for each row, right? And that the MVCC system, that multi-version concurrency control system, means we're going to have multiple copies of the same row in the heap, potentially, right? Postgres has metadata columns to track which transaction can see which, and it uses some of these other metadata columns to sort that MVCC stuff out. In this particular case, within the heap, so I've shown the Xmin column here, it's one of the ones that is involved in that particular operation, right, that's used at times for this. Let me throw a little bit of jargon at you because I'll use this term, and I just want to make sure you understand what it is. There are a number of metadata columns. I don't show them all that Postgres uses to determine a row's visibility. And you'll hear that term a lot, visibility in the Postgres world, right? And we're talking about which transactions, which rows on the table, which rows with, on disk and within the system are visible to which transactions, right? That visibility information is going to determine the transactions that can see which rows, and that's why you can have multiple rows at the same time visible to different transactions in the system, right? And that can be both for active queries or data stored on disk. It's tracking all of that kind of behind the scenes. Again, most of the time, you'll never see that stuff. Developers, query writers don't ever have to get into the weeds with that. If you go deep enough into the DBA world, you will. And so that's why I want to make sure, one, that you know about these things, and then two, understand that term visibility, because we'll be talking about that quite a bit more. So the main thing to understand, we have these visibility columns in the heap. We don't have those columns in the index, right? Remember I said there was a CTID in the index that can point back to the heap. That's how Postgres knows which row in an index belongs to which row in the heap, right? And that's how it tracks that directly. But one of the things it also has to be able to do is go back to the heap to get the visibility information. The information is complex enough that it's stored over there, and we don't keep it in the indexes. What that means is, if you're putting this together, you're starting to see every time we use an index to look up data, that means we still have to go back and verify visibility with our table. Now, it's not a one-for-one row lookup, right? It's not exactly like the same number of rows that you get means a specific row. Postgres, again, has optimizations behind the scenes that can help make that process faster. Uh, and like, we're not going to dive way too deep in that, but understand that it's not just as simple as if the data is in the index, all we ever have to do is look at the index. You're still going to have to go back and look at pages, related to the table, right? There's still going to be extra disk activity that's going on. This is a bit confusing for most people as they start to understand what's going on under the hood with Postgres. And I mean, honestly, I'll tell you, Postgres, it's my go-to database. You probably all figure that, right? When you hear people say tuning is more of an art than a science, well, I don't know if it's 100% more of an art than a science. I feel like there's some type of engineering involved. But this is part of the reason why people will say that. You can't just determine which is going to be faster looking at the number of buffers. And you might think that that would be a reasonable approach. The fewer pages I have to read on disk, well, the faster the system should be. But all of that information is not exposed that plainly. And there's this extra work, like with indexes and heaps, that can go on behind the scenes. So you just have to be prepared for that. In this case, again, our index plan may read more buffers, but it is definitely a faster plan. All right, we've got 5 seconds to do this without the index, and only just over a second with our index version. So definitely better. I also want to say, if you look at it, though, the cost parameters do align with this, right? So always keep an eye on costs as well. Postgres understands that a heap scan is going to take longer than an index scan. It's not confused about that point, right? It gave us a higher cost. And there are knobs that can control this kind of relationship. So you can do some server tuning. If we're doing a class on server tuning, like that's what would be in there, is how to tune those knobs and that kind of stuff. But in this case, like, the query bucks are showing us the right thing. This is why the query cost, right, the estimated cost that Postgres comes up with, is actually higher on the sort version, and why it chooses to use the index. Now, the thing is, there's a limit to when it's going to pick the index versus when it's going to do a sequential scan, right? Again, there's a trade-off, even in this calculation, that it has to do. There's a particular term people like to use, which is known as a covering index. And this speaks to this trade-off that you have. In some cases, a query there'll be an index that has all the data that it needs to answer that query. That's what we have provided, right? The index that we have created with both the access date and the ID is a covering index for the query that we're running, where we ask for the ID sorted by last access date, right? We have all the columns that we need to answer the query in our index. It's not a different type of index. You'll hear this term a lot, and it's used for all kinds of database systems, not just Postgres. So you'll hear this term a lot, and be aware of that. It's not a different type of index. It's not built with some special flags or anything. It's this sort of DBA jargon. I mean, do you have a covering index? Do you have an index that actually has all the information you need to answer the query? Right? And so we have one here, but even with a covering index, right, that's the ideal case, as we'll have all the data in the index, so Postgres can just focus on the index. Even with a covering index, Postgres doesn't always use that index. It might still use the heap. If you imagine changing the query like this, right? So I'm going to change the where clause to say, give me all the IDs from users where the last access date is greater than 1920, March 11th. All right. Now, FYI, I guess, in case you weren't aware, Stack Overflow didn't exist 100 years ago. So we know, right? If I said, can you give me every row that was last access date is since 1920, instead of 2020, if it's since 1920, we're going to get all the rows back. We know that, right? We can reason about that. And in theory, we have the perfect index for that, right? We have an index that has last access date and ID. So if you just scan that entire index, that would give us all the information. We have a covering index even for this query. However, if we were to run this query, Postgres is going to choose sequential scan to give us that in order to avoid that visibility lookup. And we can prove that, right? So here we are, we're going to run the query again, select ID from users, for our last access date greater than 1920, March 11th. So we've gone 100 years back in time. And it chooses this sequential scan on our users table. And you'll notice it's getting back its 12 million rows, which is how many rows we had in our users table. Right? So it's bringing everything back. It takes about 3 seconds for this query to run on my system. And again, the thing that Postgres is thinking here is that if I were to scan every row in that index, I got to go verify every row is actually visible to this transaction. If I'm going to do that for every row, I might as well just sequentially scan it. If we take a look at our explain analyze after using our sledgehammer knob and saying, hey, garbage goes out Thursday, let's turn sequential scans off. All right, so I'm saying, Postgres, if you have any other way to do this, let's not use a sequential scan. If there were no indexes, it would still do it. But in our case, we have an index, so we forced it to go use that index, right? And what we end up is it goes back to the other plan, right? The plan from our first example. Now we're still doing 1920, right? We're still 100 years ago, but we get an index-only scan, which is what we got before. The thing is, if you look at the cost of this, you can see it's at 410,000. That's what Postgres calculates for the index-only scan. On that sequential scan, it was 335,000. So it does the math, right? And there's a lot of math going on there, but it does the math and it comes up with doing this from the heap and just doing the heap and not bothering with the index should be cheaper, right? In QueryBugs terms, should be cheaper than going to the index and then having to figure out the visibility. And if we look at the execution time, we do see it is actually faster, right? Using the index-only scan gives us about 3.5 seconds. Our original query was about 3 seconds. That's not a lot, but it could make or break the difference. Depends on what your SLAs are and all that jazz, right? But the point is that Postgres is making the calculation and is coming to the right conclusion. What this means more practically is it is also not quite as simple as just saying, just index everything, right? There are trade-offs that are going to be involved. Sometimes you will add indexes to things and it won't actually get faster and you'll want to know why. If you're trying to look at statistics on your database, you say, oh, why are these tables all being sequentially scanned? Well, it might be because the nature of the queries running against them lead to saying it's faster to just sequential scan the table rather than try to do this through indexes. Right? There are trade-offs involved there. All right, let's sum that up a little bit. Let's make sure you got all that as before we move forward here. Remember, so indexes are essentially a copy of some parts of the table. We designate what those parts are when we define the columns that are going to be in those indexes. The upside of the index is that it reduces reads, generally speaking, right? And we also remove CPU for sorts if we have sort operations. The bad part being, well, because we're increasing our disk footprint and all that, right, that's going to slow down insert, update, delete work by adding those indexes in. It might make insert, update, delete queries faster, potentially, but the overall amount of work that has to be done is more work for a given insert, which means that the sort of physical writing piece of that, it's doing more work, and that part can get slower. I want you also to remember indexes don't track visibility information. This is a big difference between Postgres and, the vast majority of databases that are out there. There's a lot of different systems, and we'll talk a little bit more about that for this MVCC bit that are out there. And in the Postgres one, we don't have visibility information in our indexes, so that results with some extra back and forth with the heap, even though there is optimizations going on there to try to make that better and as minimal a hit. But it's not nothing. There's a real cost there. And the other part, again, is that query tuning in Postgres, right, that art science argument, the big thing is it really takes looking at the cost to understand why Postgres gets the answers it does and why it's choosing what it chooses. Looking at the buffers sometimes to understand what is the actual work that happened under the hood. But because there's buffer information that can come back, because that can be possibly misleading if you don't quite understand what's going on with those numbers, you also have to look at query times just to be 100% honest. Like, that's the worst measure in the sense that if you're trying to just not do everything in production, right, at the right time with the right workload, you'd love to be able to do that someplace else, but sometimes you just have to go back and look at the query times to understand which one of these things is going to be faster. All right, so I know that was a bit. Let's kick it up one more notch here. We're going to add a couple more columns back into our query. In this case, we're going to add in the display name and the reputation. Right? And now that you've seen that interplay between indexes and heap, I want you to think about how would you get the data for this query. We have an index, right? We have data over here that has our ID and our last access date. So we have indexes on that, and we have a copy of the row in our heap as well. So we have both of these. So we could use the index. Maybe we don't want to use the index. Would you use the index? That is the question. We know we are going to have to go to the heap, though, right? Like, we do understand that. So one execution plan you might come up with, right, is you would grab the last access date ID index, and thinking back to that, our little post-it note work, we'll go ahead and we'll just write down the CTID, the ID, and the last access date for all the rows that match based on our 2020 March 11th date condition. And then once we have that CTID, we can just quickly go back over to the heap and grab the other columns, along with the ID and last access date that we already have, grab those other columns and give that information back, right? Based on the CTID. We can get there pretty quickly. So that's one execution plan you could come up with. And when we run Postgres, explain analyze, we see, oh, hey, look at that. Index scan on the user's last access date ID index is what it chooses. So it's not an index only scan because it does have to go back to the heap, right? So just note that. And that makes sense, right? We know it doesn't have the column data for the other columns that we need. We knew it was going to have to go back to the heap for that. Now, you might say, well, okay, that's pretty good. If we wanted to make this faster, we wanted the index only, maybe if the columns were small, or if we were querying on those columns a lot, like if this is a one-off query where we've added display name and reputation, that's one thing. If we were querying those all the time, maybe you want to add them to the index, and we'll talk about that in a little bit. But first, I got to tell you, I actually have a confession to make. I sort of cheated to get that last explain plan. Some of you may have picked up on that before I've mentioned it. So I actually changed the last access date there from 2020, the original query, to 3020. And obviously nobody, I guess there are no time travelers that are being tracked within Stack Overflow, so nobody has actually, that's a different Stack Overflow. That's a different Stack Exchange, time travel Stack Exchange website. So this is actually not going to produce any rows. We know that logically, right? This is not going to get you any rows because nobody has access. Their last date was not in the future. Postgres does estimate a small number of rows on this, right? Hey, good job, Postgres. I like that. It estimates one. He said, I don't know, maybe I'll probably get one row back. If you're asking, I'm probably going to get a row back. I don't think there's any rows in there. But you would be asking, you must be asking for a reason. So, and it actually gets 0 rows back, which we can see with our conditional of 3020 March 11. Now, this makes sense, right? It took the index, did real quick, and then how many rows it had? If it's hey, I was only going to have to go look up one row. So visibility, extra columns, that's easy. If there were a lot of rows, though, like in our actual 2020 based query, this would actually be something a little bit different. All right, so here's the explain analyze from our real query. Here, Postgres thinks about that trade-off, right? Looks at the index versus the heap, which way do I want to go, and says, oh, you know what? I'm going to get a bunch of rows back here. And I don't think it's actually worth it to go back and forth between the index and the heap, right? I'm just going to go ahead and scan the heap. Here, we've got a parallel sequential scan, so it parallelizes that sequential scan operation, and it gives us an answer back in about 2 seconds. That's pretty good. Right, that's the decision that it decides to make. And that's the thing is there is that tipping point where if you get enough rows that are coming back, when it said, hey, I was only going to get like 1 row back, let's just use the index. Here, it's estimating, it's going to get millions of rows back. And so for that reason, it says, hey, I'm going to sequentially scan that. And again, right, the larger that number gets, we're pushing it towards saying, hey, just use the heap and that'll be faster. And again, we can prove this, right? We can see exactly what's going to happen. Get our sledgehammer, beat on Postgres a little, say, hey, don't use a sequential scan. I want you to use the index. If I run that query on my system with the sequential scans off, it gives me the index scan, right? It still has to go back to the heap to get those other columns. So it has to do an index, can't do an index only, right? And our execution time goes up. And the thing is, like, our plan is definitely simpler here, right? Like, we're not doing all the parallelizing, gathering that stuff back, and there were sorts and all that. Even though we have simplified this dramatically, it is still actually slower. And so Postgres's decision-making has borne that out, right? Our execution time here now goes up to like 8.5 seconds. So it's, almost 3 times slower to go this route. Just because the plan is simpler doesn't mean it's going to be faster, right? You have to keep that in mind. Postgres is doing that calculation for us. And this is kind of the thing. Like, Postgres is always thinking about these trade-offs. Does it scan the heap, right? If it scans the heap, that's essentially a fixed known cost to read all those rows. It knows how many rows are in the heap, right? It has a pretty good idea of that. It knows it's going to take how much time it's going to take to do the heap scan. And as it's scanning that, the rows that are removed from the filter, right, the rows that are filtered out because they don't match our where clause, that doesn't really affect the performance. It's scanning the entire heap anyways. It's not a variable, right? It's sort of, again, it's like a fixed thing. I go scan the heap and I'll have a number of rows that I get back. With the index scan, though, it's a little more volatile, right? Essentially, if I have an index scan, I know I'm going to have some visibility lookup action that I have to do. And if I also have key lookup action that I have to do, right? If I have to go get extra columns that are not in my index back from the heap, well, I don't know necessarily how many. I've got a guess as to how many it's going to be. I don't know 100% how much extra work I'm going to have to do on that sort of lookup piece, right? If I'm scanning the whole table, I'm scanning it one way or the other. If I'm doing an index scan, maybe I only need a small portion of that. So even though those index scans would be cheaper, those key lookups, right, for every row we get, we've got to go get the extra data that we have back in the table, plus the visibility checking. For a lot of rows, that ends up being worse than a table scan. Life is a series of trade-offs, even for Postgres. So, again, looking at the plans for these, right, this is, I'm comparing the 2020 plan versus our 3020 plan. Over 2 million rows it expects to get back with the 2020 plan, right? That's the last access greater than March 11th of 2020. 1 row is expected to get back, right? In the variable cost, it says, hey, like, it's going to be 1 row. I might be off by some number, but even if I'm off, probably that's going to work out, right? And really, to look at this, you have to take all the different variables involved, right? That's what Postgres is doing. It's thinking about the buffers that are going to be read, CPU operations that are going to be needed, right? It multiplies those estimates times the row estimates, figures out all the different ways that are possible to do this. It could do this either way. We know that it could generate both plans while it's doing its planning, and then it has to guess which one makes the most sense. And the key thing is it has to actually commit to that before it starts executing the query, right? That is really what makes this so tricky for Postgres. As it does its query planning work, right? Phase 1 is where it builds the execution plan for the statement, right? It's where it decides if it's going to do the scan in the heap or go use indexes, those different pieces, right? In phase 2, it actually goes and runs that. And the problem is there's no interplay between those phases. There's a very hard fence between execution planning, right, and doing the query plan and creating that, and actually executing the query itself and making that work. You can't go back, halfway through. If it's I'm scanning the index here and I'm seeing, like, I thought it was going to be, a few rows and I'm getting a ton back, maybe I should switch back over to the other plan. It cannot do that. Once it's started on the plan that it's built, it has to stick to it. It has to commit to that and keep going with it, even if it's wrong, right? There's a hard line between building that plan and executing the plan. I often think of this as I lived in a town in upstate New York called Horseheads, of all things. And if you ever go on the highway, I think they call it Interstate 83 now. Used to be the old Route 17 when I lived there. Well, they built a bypass for the interstate highway through the town where that was. And you hear these stories and you don't really believe this happens, but this one definitely happened. And, I was there before they built these bridges. So the bypass bridge that they built, somebody drew a plan, and then they handed the plan out to the builders, and they started on one end on one side and started on one end on the other side. And when they got to the middle, they didn't actually quite follow the plan correctly. So there was a little bit of there's a chicane in the highway there where they actually had to skew to get those two sides to match up. And I think most people probably assume there's some good reason for that. And the reason was, no, they actually just didn't follow the plans very well. And so this is the thing, right? Like Postgres, ideally for the highway people, what they would have loved, I'm sure, was, oh, no, we'll just, move the whole thing over one way, the other. Or we'll go back and we'll change the thing. Yeah, you can't do that. You've already started building. Like, you get to the end and you realize those two sides aren't aligned. Like, you gotta live with it. And this is the thing, right? When Postgres is doing its planning work, there's an amazing amount of work, really, that is needed to generate the plan. First, it has to build a plan, right? It has to come up with the first way in order to answer the question that you pose to it, right? To answer your query. Sum up all the different cost operations that are going to happen with that, like if there's sorts involved and whatnot, like it's got to make estimates for all of that. And once it has the cost of that, right, it comes up with a query box number. Once it has the cost of that, then it has to go and figure out, like, hey, is there another way I could do this, right? And presuming you have an index, and one of the options is to use the index, there's always a second way because you could just not use the index, right? And the more indexes you have, the more possible plans there might be. And every time there's a new possible plan, it has to go back and, again, build a new plan. Take that new option, build a plan for that, sum up all the costs of those operations. Once it gets done going through all these, out of all those plans, it's going to choose the one with the lowest cost, right? Based on those query box estimates that it's coming up with, that's how it's going to choose. And it does this over and over again. Another bit of jargon. When you hear people talk about this method, where you're creating execution plans and you're doing cost estimates on the different operations within those plans, right? This is known as a cost-based optimizer when it comes to databases. In the before times, many, many years ago, there were a lot of databases who used like rule-based optimizers. So it was, they just had a sort of strict set of rules that they would follow in order to come up with query plans. And, that's great, but pretty much I would say, all modern databases, quote unquote, all modern databases, and even NoSQL databases, they've moved to cost-based optimizers. And if you go look in the Postgres docs, there's actually a link to some of those papers that are out there talking about cost-based optimizers and the optimizer in Postgres and where it got, some of its information from. And of course, if you really want to get deep into it, you have the source code, so you can go look in the source code. There are comments in the source code. You don't just have to go look at the code. There are comments in the source code that talk about how the optimizer works, and we'll give you some information like that. So that's, another sort of avenue you can go down. So, but just be aware, if you ever hear that term cost-based optimizer, Postgres has one. And this is what it means. It's basically figuring out how many plans are available, coming up with the cost for each one, and then picking the one with the lowest cost. Absolutely simplifying that, right? The whole optimizer piece and the planning piece, even the planning bits, like it is doing all those operations. I'm still simplifying that, like a lot. Sometimes planning is trivial. Our queries have not been super long and complicated, so some of these are not that hard to plan, especially before you put indexes on, right? If I just select all from users, like that's pretty simple to plan. It's not always obvious though, how you're going to use these plans. Some of these plans could be, more complicated. If they're cheap enough to run, if they're, small enough, Postgres can stop building more plans. It sees, oh, these are obviously, anything that uses this one index that's really not accurate, it's never going to be good enough, right? So if it can build enough plans and it seems like this one's going to be cheap enough, it can go ahead and go with that good enough plan, right? That's what Postgres is trying to come to. Um, but I would say sometimes a plan actually can be so complicated on the other end of the spectrum. Actually, Postgres has a special system known as the genetic query optimizer, and again, there's info on this in the docs to figure out how to choose a plan when it's that complicated. And this is like when you start getting up above probably 8 or more tables, that type of thing, multiple indexes involved, and all that stuff. Like then it may flip over to this even more kind of out there way of doing this plan estimation. Thing to keep in mind here, though, Postgres doesn't really know when you give it a query, right? We've talked about this before. It doesn't know how many times you're going to want to run that query, right? It doesn't know whether it should just build that plan like you're going to run that query once, or maybe you're going to run it, hundreds of thousands of times. In an ideal world, I feel like we say that a lot, Postgres could review plans versus the execution times that have happened. That would be fantastic. And then say, oh, you know what, I got this wrong. The execution ended up being wildly different from what I expected to get when I planned it, and use that knowledge to improve future plans. Postgres cannot do that. Maybe someday. If those estimates are wrong, that would be the ideal thing, is just say like, hey, at this point, the estimate is wrong, right? On the initial scan that I've done or something like that, let me go revise that plan with this new data. But it cannot do that. Once Postgres makes a plan, it says, hey, we're going to do this, right? It is ride or die time. It has drawn a blood pact and said, this is the plan we're going to go with, and it's got to use that plan. It doesn't have any other option. And again, that's maybe the plan is good, but it's good or bad. It has to do that. Whether you run that query one time or a million times, it's going to go with that plan. So, as I'm talking about plans and the costs and how it's generated the cost of that, you might be sort of like, so where is it getting these numbers from? You mentioned a few times there's some knobs and whatnot that can be tuned. Well, let's talk a little bit about how Postgres is getting the numbers that it's getting. Postgres is actually behind the scenes, right, as many things are. It's collecting statistical data about all kinds of things in the system. There is just so there are dozens of system tables that are dealing with different statistics and informational purposes of what's going on within the Postgres system itself, storing all kinds of information about the tables that you have. When you add data into Postgres, right, Postgres starts to calculate statistics on that data. Usually this happens automatically behind the scenes. There's some processes you may have heard of, auto vacuum or auto analyze. Those will just kick off every now and then and start doing these analysis pieces and updating some of the statistics information within Postgres. You can also force this manually. If you go asking somebody for help on a mailing list or Slack channel or something, oftentimes people ask you, have you analyzed your data lately? Right? They want to see if you've actually updated your statistics. And these statistics are useful for Postgres for all kinds of things, right? Like it's going to decide which indexes should be used. If you have multiple tables in a query, like which order to process those tables in, whether to use sequential scans versus index scans. Main thing, one of the key parts is it's going to use that to estimate how many rows will match your query. And it's, as you get more advanced plans and you sort of look at differences like should it merge join or hash join, that kind of stuff, it's doing some math on that. And some of these numbers are coming out of these statistics tables. Right, and there's actually a whole bunch more that can be going on under there and things that you can see. The one that I usually point people towards first is the PG stats view. All right, this is based around what is the data that's actually in the table. There are other tables where Postgres will store things like the number of rows or like how many times a table has been how many times an index has been scanned or how many times a table has been scanned or, those kinds of pieces of information. In this particular view, though, this is actually about the data that's in the table itself, right? And I would say that, by default, Postgres are going to store data about every column in your table, right? Because it doesn't know which columns you're going to actually need to look at. So by default, you put a table in there, you start putting data in, it's going to, you do an analyze on that, it'll grab statistics about every column in that table. The better you understand your data, probably the less likely you would be to need to know what I'm about to tell you about. I can tell you as a consultant, though, I was in PG Stats, I would say on a regular basis. And the thing about, having access to information, knowing that it's here, the thing that I really needed to be able to do is verify if Postgres saw the data the same way that my clients thought about the data, right? And I would say if you manage, one database, or you're managing a small number of databases, you might understand your data profile well enough that you don't need to look at statistical data about your data, right? You'll know, you'll know if data is unique in a given column versus something else, right? Like you might just know that about your data. But the more databases you have to manage, right? If you're managing dozens of databases that are out there, or if you're just working with dev teams sporadically, right? If you're the go-to database person in your organization or on that team, database reliability engineering teams often, they got to drop in and go work with a team that they may have not worked with before. Knowing that you can look at this data and kind of verify that what people are telling you is actually true is invaluable. It's kind of like in the movie there, Tom Cruise, says the line, it doesn't matter what he believes, it only matters what he can prove to Postgres, right? This is what Postgres thinks is going on with your data. So you can tell me all kinds of things about, no, this is what the data looks like, here's how it breaks down, whatever. Even if you're right that that's how it should be, that doesn't mean that's how Postgres sees it. So this, being able to prove what Postgres is seeing, that's key. If you were going to do an analyze on your table, one thing you'll notice, by default, Postgres is going to scan up to 30,000 pages, right? So it'll cover a pretty large amount of data, just out of the gate. And that's a pretty decent number. You'd say, well, why is it 30,000? Is that it's a very even number. Who picked that out of a hat or whatever? And that's the nice thing about open source. So we can actually go look up the reason. Proprietary software, I often feel like they stick these numbers in places. You'll see some multiple, and you're like, well, what does that number come from? Well, we can actually go look this stuff up because we have the source code. 30,000 in this case is 100 times 300 gets us 30,000. The 100 is a planning knob that Postgres gives us called the default statistics target. And that is basically how many buckets of information would you like me to keep about a given column? Right? And we say by default, you're going to go for 100 buckets of data, right? The 300 is actually derived from a research paper that was done way back in 1998. So, turn of the century type times. And put a link in the slide to the Doxygen Postgres URL. So you can actually go look in there. The paper is random sampling for histogram construction. How much is enough? So these three folks worked on trying to figure out hey, at what point, if I'm trying to build histograms about the data that I have and understand how much data is in there, at what point is it enough? How many samples do I need in order to make this thing work? And so the 300 number is actually derived from that. So if you want to go read the paper, you can actually go read the paper, right? That's pretty awesome. And that's a link to where in the source code you'll see the reference to that paper. So that is on the main line. So that Doxygen will go to trunk of Postgres. So, it's right around that spot if you're running an older version, but it's the same paper since 1998. So whichever version of Postgres you're running, this is, it's based on that work. So, and again, so what PG Stats is going to show us, right, is that when Postgres analyzes, it takes a sample of our data. It takes 30,000 pages. Just to be clear, there's 100 and almost 180,000 pages, right, we've said, in our users table. So we looked at 30,000 out of the 180,000. And, we can kind of look at some of the information that's in there. We've got, null fractions. This is what percentage of the values in here are nulls. The width of the rows that are in there. For something like an ID, it's going to be 4, and that's fixed because it's an ID number. For other things, it'll be variable, but that gives you the average width. It'll talk about how distinct is the data in the table, right? So an ID in this case is guaranteed unique. It's the primary key. So that's in there. And then other things, the most common value, frequency, some histogram bounds. That's another kind of key one. As Postgres is analyzing, right, it's pulling a sample of pages. It takes the information it finds for each column, condenses that into a single row per column, which it then stores and exposes that back through pgstats, amongst other places potentially. And then it uses that information to determine what information it needs to get when it's given a query, right? So for example, the estimated number of rows for a query. If we look at the query we've been looking at, which is that 2020 March 11th, right, boundary for our last access date, and I've said, like, what the first thing it wants to do is figure out how many rows should I expect back, right? With the 3020, it's probably at least one. But in this case, so with 2020, how does it come up with the number it wants? Well, the plan that Postgres is going to pick, as we've shown, is going to be dependent on how many rows it thinks it's going to get back. And the way that it's figuring this out is it's looking in pgstats in this histogram bounds table. And if you look in there, you'll see like there's all these different buckets of dates. These are spread evenly across the entire range of dates that are in there. And so you see like it goes all the way back. There's a bucket of 2009, and the next one is 2011. Which there's like a 2-year gap in that first bucket, which makes sense because you would expect that most of the people who have accessed it more recently than 2009. So that's a small number, and that's on the one end of it. And these are in order, so they get larger as you go from, the first entry. This is essentially an array of data. It gets larger as you go from the first entry to the last one. What it's basically doing though is it's looking through these histogram bounds until it finds the two buckets that bound, are the boundary for the date that we're looking at. So we were looking for March 20th of March 11th of 2020. That falls between this bucket of March 8th and the other bucket of March 18th, right? That's where we're on March 11th. So it knows, hey, I got to start in this one bucket, the March 8th bucket, but then anything, since we're just looking for what's greater than that, then anything after that, the next bucket is larger, and so it's off to the races to get all those remaining buckets, right? That's how Postgres is going to start its calculation, because it knows all those other buckets must have rows that correspond. How does this work in practice? Well, we can see in our explain analyze, right? Last access date greater than March 11th of 2020. The estimated rows here is 2,263,000 approximately. It comes up with 2,726,000 is the actual number of rows that we got. That's pretty good, I would say. So we know there's 12 million rows in the table. So it's off by 50,000, but that's 0.5% of the total number of rows in the table. So it's certainly, it's in the right ballpark, as they like to say. That's not bad at all. From its first guess to the second one, right, to the actual number of rows. The good part about this, right, and golf clap if you want for Postgres, like getting that close, the key though here is we had statistics on the last access date column. You can actually force Postgres to not gather statistics on columns if you want. But we had statistics on there, and we knew those statistics were up to date and accurately sampled, right? We have the advantage here that we're using a static copy, or mostly static copy of the database. So this is from May of 2020, this version that I've used. If you can imagine, if you were to get a new dump from Stack Overflow, import that in, those numbers will have shifted since then, obviously. Also, our query was actually pretty easy to understand, right? It's a simple where clause, one column, one value that it's got to compare against. It just goes and looks that up. And so, we weren't doing any calculations or weird functions or anything like that on that date column. So that makes it easier to do that computation for Postgres. Of course, Postgres doing a good job is not why you're here. You're here for when Postgres has issues. So it is possible your statistics could be out of date, right? How often you sample your data in your system, right? That's going to work to how up to date the information is in our statistics tables. The other thing that can hit you sometimes, so you want to be analyzing frequently enough to make sure that your statistics don't get out of date. The other thing that could be weird, though, is that sometimes you get a poor sample of statistics, right? Essentially, and there's, again, if you were to go read in the source and whatnot, look and see, there's algorithms that Postgres uses to pick the pages that it's going to pick. It doesn't just pick like the first 30,000 that it sees, right? It's trying to do a random sample across the number of pages. And it's possible, I've certainly seen this out in the wild, where Postgres will pick a poor sample given the data distribution that we have. As you can imagine, if it's an insert-only table, that's pretty easy to reason about, that the oldest rows are at the beginning and the newest rows are at the end. But as things are being updated and deleted and whatnot, like that becomes a much harder thing to figure out. So you can get poorly sampled, where it just happens to get some weird skew of representation based on the random, again, it's picking quasi-random pages, so that can happen. Another thing, of course, the query might not be as easy to understand. And when I say that, I don't mean like it just may be a more complicated query. That, of course, could be true. Right? We could have a lot of tables and joins and all that stuff. But take a look at these two queries. So these two queries, let me walk you through. This isn't the exact same query that we've used before. It's slightly different. So here what I want is the ID, display name, and reputation from users. But I want everything where the last access date is greater than or equal to March of 2016. Right? So we're going back a number of years. But also where the last access date is less than April 1st of 2016. Right? I'm basically looking for all the rows that happened in March of 2016. I'm going to order those by the last access date. Right? If you look at that second query, we're kind of doing something pretty similar. Here we're using a couple of functions that Postgres has, called datepart, and we pass in parameters so that we say, like, well, I want you to use datepart on the last access date for the year. I want that to match 2016, and give me the datepart, meaning the month part of last access date, and have that equal to 3. You and I can reason about these two queries and say both of these are going to produce the same thing. Anyone with a last access date that falls into March of 2016, we're going to get those rows back. Right? We can reason about that. Postgres cannot. Right? Let's look at the explain plan for these two queries. In the first one, this looks pretty normal. Right? We have our last access date between March 1st, 2016 and less than April 1st of 2016. And what we see, Postgres, it comes up with an estimate of 72,000 rows is what it thinks is going to be the right number of rows. And this is, again, this is just explained, just so you understand. I just want to look at what were the plans it came up with. It thinks, well, I will do a bitmap index scan on our last access ID index. And that's basically another type of index scanning they can do. It's faster than a regular index scan, potentially. And then it goes back and does some visibility, verification, that type of stuff, double checking the values that it puts in there. So it's going to use the index, right? That's the bottom line. It just says, hey, 72,000 rows is what I expect. I'm going to use the index to answer this query. We'll see how fast that goes. But look at the other one. With the date part, right, when we use the functions in there, Postgres comes up with a different idea. We'll put it that way. That's one way to put it. So it thinks it's only going to get back 260 rows. And when it says, I'm only going to get 260 rows, I think I will just scan the table, right? And I'll parallelize that. So maybe doing parallel scanning of the table could be faster than doing the index. The thing that's tricky about this is looking at these two queries, which of these do you actually think is correct? If you just look at the row estimates, right, 2016 is like 6 years ago plus. So do you think there were 72,000 people who actually last accessed the system, 6 years ago that are in that table? I don't know. That number sounds awful high to me. On the other hand, 260 sounds pretty low. So, just looking at those estimates, we don't necessarily know which one of these is correct. I think either of them could be correct. best way to find out, I suppose, let's run the explain analyze. So here's our first one, and this one kind of, the gig is up here. So in the first query where I, very clearly laid out, I want a last access date greater than or equal to March 1st of 2016, or I want the last access date to be less than 2016 April 1st, right? So give me those March ones of 2016. When I laid that out clearly, spelled it all out, gave the dates and everything, Postgres estimated 72,000 rows. It actually gets back 88,880 for the final result. And if you look even further down, when it decided to do that bitmap index scan, it's actually even closer, right? Like it estimates there that from the bitmap index scan, I'll get 86,958, and it gets back it's 88,888. That's actually phenomenal that it got that close, right? It's only off by like a couple hundred. That's pretty good. When you're measuring the hundreds, a little low thousand, that's fantastic. And the upper one, 72,000 versus 88,000, like, hey, again, we are in the right ballpark to say the least. Of course, this kind of spells some bad news when it comes to our other query. If we know those queries were the same, then hey, maybe they weren't the same. Maybe something went magically wrong and we reasoned about things incorrectly. Or maybe Postgres reasoned incorrectly. So when we run the explain analyze on this query, right, with our date functions, like we're not only not in the right ballpark, like we're not even playing the right sport, right? Postgres tries to figure out, it's happy to make a guess about how this is going to work out. It's happy to make a guess about it. It says 260 rows is what I expect to get back. It does actually get back its 88,880, just like the other query. So we were right. These are the same query. They will produce the same results. For its parallel sequential scanning, you see, well, it's going to do it in parallel. So it thought, well, one worker is going to give me 130 rows and the other one will give me 130 rows. That'll give me 260. It'll be great, right? But we actually see, like, oh no, those scans are like, it's way off. So it's nice. Postgres took a guess at it. Kind of got it wrong. But he does give you the right answer. Like, that's the thing. That is important to remember. Both of these queries produce the right answer, even though it go about it very different ways. Right? They both get you those 88,000 rows. This is actually kind of a difficult point sometimes for developers to get past. This causes a lot of frustration that, hey, like if I'm smart enough to know that these two queries should produce the same result, like why doesn't Postgres do the same thing? And it's like, hey, Postgres was smart enough to get you the right answer. But it doesn't do the same thing. Like, hey, all your code should be bug-free and never have performance issues either, right? Like, hey, that's the nature of the work that we do. I would just say, like, as a query writer, you need to understand that the more shortcuts you take when you're writing your queries, right? When you do things like put these functions in and whatnot, you are increasing the likelihood that Postgres might get confused about what it is you're trying to accomplish and be confused about how best to answer your queries or even what the options are for answering your queries. So, when you're writing these kinds of queries, make sure that you take the time to go ahead and write them well. You want, well-crafted code, as they say, but in this case, our code is SQL. So make sure you're doing well-crafted SQL. I also want to make sure you understand, like, it isn't that Postgres can't use, functions with indexes or some weird thing like that. So, let me grab the sledgehammer and kind of beat on it a bit. Say, hey, don't use sequential scans. Let me run, what is your plan? If I said that you can't sequential scan, what would your plan have been for, this function version of the query? And it will try to use the index scan. It does a parallel index scan. You see that its estimates are still off. Like, they're, I guess, technically better. It estimates 130 rows coming back from each index. We saw that trick before. And the total estimate is 312. Hey, that's more accurate than 260. But, it's not really accurate. So Postgres can use indexes. It's doing cost calculations and trying to figure that stuff out. All right, and that's the thing. It is complicated work that Postgres is doing. That's why we have Postgres do it. It has to calculate things like the number of rows in the result, where's the data, is it in the index or the heap? Has to think about visibility of those rows in the index. It has to calculate I/O of sort steps, like what is the likelihood of doing merge versus, like writing to disk. It have to sort that stuff out. There's CPU overhead in function calls. It does do calculations based on that. The more often it's going to have to call a function, it understands that that is a factor it has to deal with when it comes up with its cost estimation. Right? And just to throw you another curveball here, imagine if we change our query just a little bit. So in the previous one, we were looking at 2016, right? March of 2016. Here we're going to look at March of 2020. So this is sort of more the data that we've been dealing with, right, or closer to it. So here, what if I said, let's look for everything last access greater than or equal to March 1st of 2020 and less than April 1st of 2020, right? And by the same part, we're going to change our other query to say the year date part, we want 2020. So we're trying to get all the rows back from March of 2020 rather than 2016. Well, we know, so this is pretty close to the most recent data in our sample. This is from May of 2020. So you might have some ideas about what would be the right number to expect back. Again, like I said, we know those two queries, they're both March of 2020. We know those two queries are going to produce the same result. But again, Postgres does not know that. Postgres estimates with our clear, simple query, we're going to get back about 265,000 rows. That's what it's estimating. And we see, whoa, wait, I think we've seen this before. It's estimating 260 rows with our function-based version. Right, we're still getting the same rows. So now, given what we know about our data, right, we don't have to go verify this in the stats table. We know that 260 almost certainly is wrong because we've seen that number before, and it was really wrong. How wrong is it, as they say? Well, stop me if you've seen this one. So in our first, the clear version of the query, the nice SQL version of the query, it does a bitmap index scan as we expect. It's estimating about 317,000 rows on the index scan piece of it, getting back 330,000 about. That's really pretty good. In the query overall, it was estimating 264,000. It actually got back 329,000. That's not as good as what we had before, but it's not wildly. It's not order of magnitude off, right? And oftentimes when you're doing query tuning, this is one of the things you're looking for. Are we orders of magnitude off when it comes to our row estimation? We are orders of magnitude off when we look at our function-based version of this, right? It tries to do the sequential scan by default, and again, it's in the 130, but it's going to get hundreds of thousands of these back. 260 for the total, 329,000. We get the same answer back here, so that's good. We're getting the right answer, but obviously with a plan, it's just a bigger disparity than what we even had before. So now there's a plot twist here. So you thought you'd seen this before. It's never quite that simple. Postgres throws us yet another curveball here. So one thing I want you to look at is, notice that in the first one, our cost was just over 300,000 in query bucks, but our time was about 0.6 of a second, right? In our function-based version, here's a little thing, something's a little odd. Our cost is 284,000 query bucks. That's actually less than what we came up with for the nice SQL version of the query. But the time is almost 3 times as bad on the function version. So you might look at this and say, well, wait a minute, how is it that the faster query is actually more expensive than, in a query buck sense, how is the faster query more expensive than our slow query? Well, for better or worse, right, one of the key elements in plan cost estimation is the number of rows. So when Postgres comes up with the wrong number of rows in its estimate, there's almost like a cascading effect that happens on that. As it's doing its other calculations, right? When it says, oh, I'm going to have to do visibility or grab other data from the heap or whatever, when those rows are wrong in the estimation, then it's going to be wrong about these other things as well, right? Or at least it can be, and that can often lead to poor query times, right? Postgres can pick the wrong plan just because the estimated rows are wrong. In this case, arguably that's your fault. You've written a query that is more complicated for Postgres to understand. If you use a simpler one, it'll understand it better. It has a better shot at coming up with a good plan. And again, like I said, that's why you're looking for are the cost estimations, are those row estimations, orders of magnitude off, because then it probably means that the cost evaluation that it did wasn't really as accurate as you would want it to be. One more time, the easier you can make your queries to understand, the easier it is for like a human being to sit down and read your queries, right? To be able to come up with a decent plan to say, hey, I know what I should be doing here. The more likely you will get a plan that you want. The more likely it'll use the index that you want, or the more likely you'll get the query performance that you're looking for. But the more shortcuts you take, right? If you hand a human your query and they hand you back their 2 weeks notice, like, okay, you're probably going to get a worse execution plan. I guess the upside, at least Postgres isn't going to quit. Probably. All right, we've thrown a lot at you again. I want you to remember this. Let's drink this in a little bit, as they say. So, index versus a heap, right? Postgres is making these decisions. If a query wants more columns than we have in our indexes, that means, Postgres has to decide between those two, and it might have to go back to the heap. That tipping point is when Postgres says, hey, it's faster for me to just go scan the heap than to do the index lookups plus the heap lookups, right? And that's exacerbated by having columns that are in the heap that are not in our index. We talked about cost-based optimization, right? Postgres comes up with costs for different plans, and that's how it chooses which plan it's going to use. So you need to be aware of that if you want to understand why Postgres is picking what it's picking. And we've shown you that the simpler your SQL, the more accurate the cost estimates will be, and usually the better the plan you will get as well. It's, making decisions. You ever had to go out to dinner and, well, where do you want? I don't know. Where do you want? Oh, I don't care where you're like, oh, let's go get, Mexican. Oh, I don't want Mexican, right? Well, okay, when it comes to query planning, Postgres is the decider, right? It often is trying to choose between these two things where we're talking about scanning of tables versus index scans with its visibility and column lookups. And if you recall, our query syntax doesn't always help when it's trying to do this, right? Looking at these two, again, we knew these two will produce the same results. Postgres comes up with very different plans on how to get that. All right. Okay, so one way you could solve that is, well, why don't we make a bigger index? Right? Why don't we include all the information in there? All right, so we could do that. We'll create an index on users where we have last access date, ID, display name, and reputation. So we're adding 2 new columns in. Once that finishes, first, remember, we've now created another copy of our data. Right? So we have, for something like the last access date, it lives in the heap, lives in the first index we created, and now it lives in a second index. So we got 3 copies of that data, right? We have 2 copies of display name and 2 copies of reputation. So we've got another copy of our data in here. That probably is going to look something like this. If you were to look closely, I've got yet another page, slightly different colored, because this is a slightly different index. The thing about this is, so now we're going to have 4 columns in here: last access date, ID, display name, and reputation, along with our CTID, because we always have to have our pointers back from the index back to the table. The thing with this is, if you look at it, well, you can't actually fit as many rows on the page because we have more columns to put in. Right? This makes the index wider. It also is going to make the index bigger. This is mapping what is going on the file system as well. So, that's why the representation is there. As the rows get wider, you put fewer on a page. That means you have to have more pages to do the same number of rows. And the rows are governed primarily from the heap in these index cases. So this means the index is going to be bigger. that's not nothing. Um, in this particular case, it's a little bit under twice the size of the original index. And the reason that that's important is, again, you have to remember things like that are now going to take longer. Those inserts and deletes are going to take longer. Scanning the index in and of itself will take longer. It's longer for maintenance work that you might have to do. If you ever do like a reindex or something like that, it will take longer to do that. Vacuums will take longer because it takes longer to scan through the index. But all of that. But if you're willing to make the trade-off, it can often improve performance of your queries. So I don't want you to think it's not worth it, but be aware of the trade-offs that you're making. If we build that index, right, and then we do an explain analyze on our query, this is the 2020 version, so we want everything March of 2020, we see that we go back to the simple one operator plan, right? We get an index-only scan because now it has display name and reputation in the index. So it's very easy for Postgres to say, oh, I can get all the rows that I need out of the index. Heap fetches a 0. I don't have to go back to get any data over there. So we've eliminated all the sorts out of the plan that we would have had before, and this is actually like a 10x improvement on our index performance, right, on our query performance, because it used the indexes. But like I said, it is physically larger in memory and on disk. We've used more 8K pages to store that same number of rows. So part of this you might want to think is like, well, how bad is that trade-off? 10x improvement in query is pretty good. Is the trade-off worth it? Well, if you want to see the first, sort of best way that this impacts you is, let's look at the size of the indexes. I put together a query here that you can use for any client. If you're using PSQL, a lot of people use the command line for Postgres PSQL. That would be \di plus. Will show you indexes and their size. But here I put a query together you can run from any client. And what we're basically doing is say, give me the indexes and their size for the user table. All right, and I've used some magic Postgres sauce to get that from this query. And I said, give me the pretty version of the size, because it's just much easier to work in pretty sizes in my mind. So here we've got 3 indexes actually that are on this table. Maybe you've forgotten. So we have a primary key. We have an index for the primary key. We have an index on our last access date and ID. That's the first index we built so many moons ago. That one's 375 megs, right? So that was the size of that index. And this new one that we've just built, 573 megs. So like I said, it's not double the size. But it is, it's a couple hundred megs bigger, so it's not an insignificant amount of size. It's not 5%, 10%. Like, there's a pretty good jump there. And so we can look at that and, make some reasoning about that. And this is the thing. The more indexes that you have, the more columns are in those. Like, as we just saw, we added a couple more columns. The more space they take up in memory, that means the less other objects you can have in your shared buffers, right, or in your disk cache. Take up more space on disk. That also affects not only your primary, we're basically working on a single node here, but as you get into production and you have replicas, failover machines on that, like those machines have to be bigger as well, because it's going to take up more space over there. Backups on your system will take longer. Restores will take longer. Insert, update, and delete operations will take longer. All of that stuff. Vacuums, again, also going to take longer. So all of that stuff is going to take longer as the index size is increasing. And the thing is, that Postgres doesn't work at the row level, remember? It works at the page level. So when he has to get info from one of these indexes, like, he's got to pull pages in the RAM. And if 10 rows were on one page in one index and they're on 5 pages in the other index, that's 5 pages it's got to pull up in the RAM. And it's, again, the same thing. When it writes it, it's got to write now 5 pages it'll have to modify, or really probably 10, and flush that back to disk. So these things aren't free, right? There's trade-offs. We got 10x performance. It might be worth it. Probably is. How do you know? Well, here's a sort of a simple heuristic, I would say. You could have too many indexes. If you see people complaining about slow inserts or deletes, I would say maybe you have too many indexes. If you're using monitoring tools and you see anything around lock weights like that, that could potentially be a sign. Depends on what your app is doing, but the more indexes are involved and write activity on those indexes, there is under the hood locking that Postgres does have to do. It has to do some of that in order to keep everything straight. So that could potentially be a warning sign. And then the other one is just, if the size of your database is creating a problem. Back in the day, as they say, we often we would do database backups, and they would go to something like a tape drive. Well, the tape drive has a fixed size, so as your database size got larger, and obviously, like, you would take a backup and compress it and all that, and stick it on the tape. But usually, at some point, you would run out of space on the tape drive, and then like, oh well, we got to do something. We got to get rid of something, right? So maybe index is the answer. Maybe it's something else. But if database size is a problem, here, probably the way nowadays it would be a couple of things like if you're taking backups and storing them in like S3 or some kind of cloud object system like that, how long does it take to ship that over the network and ship it back, and what is the cost of that shipping that goes on, right? The larger your database size is, the larger the backup is, and so then the longer those things are going to take. The flip side of that, of course, is you might not have enough indexes. That is where people are complaining about slow selects, right? But not worried about insert and deletes, right? That those are too slow. If you're hearing a lot of complaints about slow selects, that probably means you need a new index someplace. Or also, again, like I said, money and hardware are the answer to so many problems with databases. So if you can cache a lot of this database in memory, it may not matter. The thing that I've run across, because I've done consulting for so long, is like people first learn about indexes and they're like, ooh, I have found the magic bullet and it is covered in secret sauce. And they just start indexing everything, right? And that might be fine at first, right? It might be great because they're fixing query performance issues by adding these indexes in. But over time, that does add up, right? That does start to weigh on Postgres and can drag down your performance. So that's the thing you have to kind of be aware of. One thing people might tell you, I've heard this a number of times, and that, I guess we need to get educated, understand the trade-offs, and maybe do a little debunking. One of the workarounds for this index size problem and making all the indexes people talk about is includes. A lot of people like includes. I mean, I don't dislike them. I think maybe they're a little overhyped at times. But some say, well, okay, rather than create bigger indexes with all these columns, we could just include columns in an index, right? And what that means, again, it's not a different type of index necessarily. It's built a little bit different, where you say, I'm going to include a couple of columns, and those will not be part of the key. So essentially, add these columns in, but let's not sort on those columns, right? If I were to create a new index, so here's the create index command, and it would be, here I'm going to call it users last access date ID includes, includes, on users, on the last access date and ID. So those two columns we're going to sort on, just like our original two-column index. Then I'm going to include display name and reputation. Right? So that means I want you to put these in the index, but I don't want you to sort on them. Right? I just want to have the data available. It's not actually part of the index itself. It's just sort of sitting there nearby. Now, personally, I was, sometimes I wonder, like, if this feature was like one of those compatibility checklist things, like somebody was moving from some other database and it had include, so like Postgres, hey, we got to have it. This actually came in Postgres 11, so people have gotten by without includes for a very long time. And, like I said, like it's not never useful, but I think maybe a little overblown. And one of the first things people say is like, well, because we're only including, we can build our indexes somewhat differently and optimize for that case, and we won't have increased the size quite so much. Well, are you sure about that? Well, so actually, we can run our query again, having built that that shows us the size of all these indexes. And here, sort of emphasis mine. So the first one is, last access ID, display name, reputation index. That's the one we have where all the columns are in the key. And the second one with the underscore inc, that's the one with our included columns. And, lo and behold, hey, these are actually the same size. And if you think about it, that actually makes a lot of sense. The largest portion of an index is actually the data that it is storing. Right? There are other pages that go into an index structure, that help with that sorting bit and B tree structure of an index and all that. But the biggest piece of that is the data it's holding, and these two indexes have all the same data, right? They still have all the same access dates, IDs, display names, and reputation for all those rows. So it makes sense that they would be pretty close in size, and here we see they're actually the same size. So moving columns in and out of the index is not going to help you if you have a space problem. If somebody suggests that to you, then you know that you don't have to listen to their suggestions anymore because that one is not any good. So these indexes are the same size, so there's not much to gain there. And the other argument people make about includes that they say all the time is, well, includes are much lighter weight, right? Because hear me out. This is sound logic. When the contents change in an index, the data doesn't have to be resorted. So that means it's a lighter weight index. There's less work that has to go on. You said more work sucks. Doing includes means we do less work, so that must be awesome. That's what they say. But is it actually true? Well, let's take a look. Say we pulled a sample of data out of our index, right? It looks something like this. We have our last access state, ID, display name, reputation, and our seated pointers back to the heap, right? If user Danny Smurf, love that name, if Danny Smurf has his answer uploaded, right? He gives an awesome answer, spot on, just perfect answer. That's fantastic. And somebody upvotes that answer, he's going to get a reputation point, right? And that's going to be added in. So instead of 479, he'll go to 480. That's really great. And the thing is, just changing that to 480, we wouldn't have to move Danny Smurf around on the page, right? He doesn't fit into a different spot someplace else. That's just an included thing. It doesn't matter what that number is. So that seems pretty good, right? We've included reputation. Reputation changed. Goes in the same spot. That seems good. I don't want you to think it's free. I should clarify. So when I say we don't have to do anything to change where it goes on the page, we still got a lot of work that we'd have to do if that were to happen, right? Postgres still has to go search for the page that this row is on, pull that page up into memory, make the changes, push that back out to disk, flush it, sync it, all that good stuff. We're writing the new data. So none of that work goes away. It's just that, where it falls in the sort order doesn't change. But if I were to have put that column in the index key, well, what would happen in that case? Well, in this version that we have, if we had done that same update to Danny Smurf's row, right? Spot on answer, good job. Where would that go on this page? Well, it actually would basically go in the same place, right? Where the reputation number doesn't affect anything. In fact, even the display name doesn't affect everything. We could change his name to Azrael's Lunch, and it would still go in the same spot because it's sorted first on last access date and then on ID. And in fact, if I change his ID, that wouldn't change where this lives, right? Because last access date, it's down to tens of nanoseconds or whatever. So that is pretty much, it's not guaranteed unique, but it's basically a unique column. So anything else that comes after that is going to sort in basically the same way, right? So it doesn't actually change where it goes on the page, which means all this extra sorting work that we're pretending that we have to do doesn't really matter. What this means essentially is that, right, key versus include, that's not the right argument. It's not the right problem to be thinking about. And that's what I want you to get out of this here, right? The first column that you put in an index, that one is just critically important, dramatic difference based on the first column of an index. And in generally, I would say you'd want that to be pretty unique. Ideally it would be a unique column, or fairly unique column at least, in order to that. It doesn't have to be 100%, but you want it to be fairly unique in there, even if it's not perfect. But that's the thing. The first 1 to 2 columns, those make a world of difference when you're talking about query performance, right? Those first 2 columns are huge. The rest of the columns after that, they matter far less. Especially the more unique those first 2 columns are. If the first one is unique, then the rest, it's great to have those columns, but from a sort perspective, right, and the CPU work and all that, the work is already done. It's unique. So, and I don't want to like completely dismiss this because, I would say, certainly in the world of databases, you've already seen a few. There's always exceptions in edge cases, right? So it's not that these things are never useful, especially includes. They can be useful, certainly in more, sort of niche cases and advanced techniques out there. They can be very useful. But the real thing is, if you get the first like couple three columns right in an index, like that's really gonna make or break you, right? And the rest are kind of only there for show. So focus on those first few columns and what they can do for you. If that's where you spend the bulk of your time, you're spending it in the right area. If you're trying to figure out like, well, which ones should I be worried about, like which go in a include versus a key, maybe I would say columns that are in like the where clause, that's the obvious one. But like a group by, or if you're joining on a particular column or doing an order by, like those are usually good candidates to have in the index key that move those closer to the front. And then columns that are only in the select, like that's good to be an include, right? To have that as an include, is to just put it in the select. Just don't think that those select ones are free, right? Just don't be like, oh, well, we're just going to start adding includes to everything because it's free. No, that, again, makes the indexes bigger, makes the backups larger, makes maintenance take longer, all of that stuff, right? And the thing is, like, in most cases, finding machines, again, 20 years of consulting, finding machines that are like CPU pegged, that cannot afford any extra CPU at all. Usually, if that's the case, an index that solves a sort problem is probably going to be what's going on there. The fact that, the CPU overhead of building indexes, like that's almost, nothing. And the CPU even on the insert to sort 3 columns versus 4 columns, that's really not generally ever contributing to the problem in that way. So that's pretty negligible thing to worry about. All right, let's sum this bit up, and then it's been a while. I'll let you get out of here. So just remember, okay, fewer columns does give you fewer benefits, right? Oftentimes, actually, queries only need 1 or 2 columns. You can go into very large systems and you'll look, and they may have, a large number of indexes, and many of those indexes will not be that large. Because 1 or 2 columns is really the key for the where clause or join order and whatnot. And so, you can often get it done on 1 or 2 columns, but you may need more in order to get more benefits, and just be aware of that. More columns, right? That, again, it's the trade-off. More columns is more problems because of bigger indexes, longer maintenance jobs, potential locking, all that stuff. And then included columns aren't magic. All right. That's everything I wanted to cover for now. I hope you've enjoyed this. I know it's a lot to digest between these 2 videos. Please go back and watch it again and again if you need to. That's totally cool. 2 big things I feel like I have to put out there. One, the Stack Overflow. They make the data dumps available for their system, and I'm able to take those. I've converted them to Postgres and built this on a Postgres system in order to be able to run these experiments. Also would have to give a big thanks to Brent Ozar, who is the person who kind of inspired me to do this. He does a very similar talk on SQL Server. So I've taken, these are his examples and whatnot that he's done for SQL Server, and I've changed them as needed to kind of show you many of the same things on Postgres. So I definitely want to thank him as well. If you have questions on this, of course, you can contact me. I am available on Twitter at RobTree2, or just leave a comment, I guess is how YouTube works, is what they say. So one more time, thank you. I hope it's been good for you, and I'll talk to you next time around. Bye.